My name is Marco Palladino. I'm the CTO and co-founder of Kong. And what I was about to say is that we're seeing it every day around us. Every product is becoming a digital product, and when they become digital, they become cloud native. The driver for every major business transformation and technological transformation is the business itself. We want to scale the business. We want to make our customers happy. Therefore, we want to build more reliable applications. And then we want to get new customers. And to do that, we try to target new markets. We try to expand our products. In order to do that effectively, we then adopt the cloud. We adopt modern technologies, modern patterns. We stand on the shoulders of giants. The application teams are relying on the architects to be building the underlying infrastructure that their products are going to be using. And running a modern infrastructure really is like running a city. The architects build the bridges, the roads, that the application teams can use to build their products. But like running a city, we need to connect different places together. We need to enable the flow of information from one building to another. We need electricity. We need police departments. We need security. We need routing. We need street lights, street signs. And the more buildings, the more products, the more infrastructure we need to make sure that everything runs in an organized way. There is no other way around this. If we don't build this infrastructure, then the individual teams will go ahead and do it themselves in a very fragmented way. Or worse, they're not going to be doing this at all, hurting the business. Sometimes it can be challenging to do all of this. Different teams are using different platforms that require different services over time. And whoever is building this infrastructure might feel overwhelmed by all of these requirements. It's all about connectivity. We are replacing the reliability of our CPUs with the unreliability of the network. We are replacing the reliability of the CPUs, of the underlying function calls, with the unreliability of the network. The more distributed and decoupled our systems become, the more network we have across each one of these different requests. We are building for a new era of software. Things have changed a lot in the past few years. Data, for example, entered a new stage. Data can be in three different stages. It can be in use by an operating system, by an application, by a monolith, or it can be at rest in a database. Monolithic applications, in a way, encourage those silos. Data is being stored and used without moving too much from one place to another. But in order to scale our business, in order to target those new markets, in order to release new products, in order to modernize what the existing experience for the existing customers, we then distribute our products in the cloud. We target new regions. And data becomes more and more in motion. It enters this new stage. In motion from one service to another, in motion from one data center to another. By 2020, we're going to be seeing a 40x increase in data in motion over a network. think about microservices, think about modern architectures. We're going to be seeing more and more decentralized architectures. We're going to be building more data centers in the world. We're going to be targeting more regions. And all of this we're doing in order to grow the business, to make existing customer happier, get new customers. Our architectures are getting smarter. The computing power has increased exponentially over the past few years. We're going to be having more IoT devices connecting to our systems. The requests are going to be coming increasingly not just from other teams, but also from more and more external clients, devices, IoT systems. And in order to deal with this increased connectivity, in order to build new modern infrastructure that can help us being successful in this new era, we can adopt patterns and technologies that can help us into building modern applications. We're transitioning from large monolithic systems to distributed, decoupled architectures like microservices and service mesh, as well as function as a service, Lambda, and who knows what's going to happen next. These patterns are helping us into building those modern architectures, into making sure that the city, the infrastructure for our city is in place. But what does it mean to transform a product, to transform an organization? Refactoring a monolith, enabling that digital transformation, is an activity that unlocks two things: team productivity and business scalability. These are keywords into being able to describe the final goals of our transformations. 86% of digital transformations fail. 86%, they're failing because they do not understand the key goals and requirements of the business. They become academic projects, and that's when they fail. But before approaching any transformation, we must ask ourselves, are we ready? Is the team ready? Is the organization ready? Is the leadership ready into understanding that this transformation, this transition will require, it's not going to happen overnight, and will require perhaps years to be completed. We're going to be moving from a simpler place, if you wish, large systems, monolithic applications, into a new state where we have hundreds, thousands of services that we want to manage. And ultimately, if the organization is ready, we'll drive more business because we'll increase the velocity on how we deploy and how we build our applications. It will increase the velocity on how we can scale the existing teams, how we can target new markets. But if the organization is not ready today into operating and successfully developing their existing systems, transitioning to a more distributed and decoupled architecture is going to be more painful, not less painful. There are different ways organizations are approaching this transition, three different strategies. The first one is the ice cream scoop strategy. We scoop out from the existing systems services that can now run independently with different technologies by different teams. Then there is another strategy, which is to keep the existing systems, the brownfield legacy applications in place as they are today, and build new greenfield modern architectures in a more modern pattern, if you wish, and connect them with the legacy brownfield, so keeping them separate. And then there is the nuclear option, which replaces all that we have today with modern decoupled distributed applications. The first one is the strategy that I've seen being more successful over time, as opposed to the second one and the third one. The third one, it's called nuclear for a reason. But before we approach every transformation, before we prepare for it, we really have to think about this as a refactoring, really. A refactoring not just of our technology, but a refactoring of our operational processes, a refactoring of our team culture. Transforming and being cloud native really is a change that impacts these three different angles: technology, operations, and people, and culture. We really need to have a clear understanding of what the current systems do and who might be impacted by this transformation. And then once we do understand that, only there, like any refactoring, only then we can transition and change how the applications work and perhaps leverage new technologies, new patterns, new programming languages to build the next era. For example, let's assume that we're building a marketplace, and a marketplace like Amazon, for example, has a few components, right? This is a monolith, and within the monolith, we do have things like user management. We do have things like billing. We do have things like reviews. And everything is in one place. As we progress the product, as we get more customers, we want to accelerate the development speed. We want to be deploying more often. We want to be creating more features, and we want to be distributing the application across the entire world. We want to be supporting more devices. We want people to be able to access our marketplace from pretty much everywhere in the world, from every client. But the monolith, it's not built for that. The monolith does not allow the business to scale that way, because different teams are going to be working together, and they require greater and greater coordination in order to make all of this working together. So we go ahead and we scoop out from the monolith the search, the inventory services, because those are the systems that require the most frequent deployments. This was the biggest pain point in the business. We wanted to scale these components, and so we extract it. And then over time, we realize that it's not enough. And so step by step in our journey, we then extract it again. And we decouple more and more our systems as the business requires it. Not all at once, but little by little, in order to be creating those little wins along the way that give confidence to the team that this is the right strategy. It gives them time to learn from their mistakes slowly, but also gives confidence to the leadership that this is the right way forward. And as we slowly decouple our systems, we realize one thing. We realize that whatever decoupling we're implementing, it's not going to be looking in a uniform, consistent way. It's going to look like this, depending on the actual requirements that the application and the business have. It's a very pragmatic journey to modernization, if you look at it. In traditional applications, monolithic applications, our systems are made of different objects, different classes that interact one with another over a CPU by leveraging function calls. And we expect those function calls to always work. The invocation, at least, that will always work. In microservices, decoupled and distributed architectures, we are replacing that CPU with the network. Our objects become services, and those function calls become API requests that go over a network in order to be consumed. And the network really is the biggest variable we have. The more information becomes in motion within the products within the organization. The network, as we all know, can fail. The network, as we all know, can be slow, it's not reliable. The network cannot be trusted. And as we make this transition, sooner than later, we'll have to address the network. We'll have to build something that allows us to manage this connectivity among different places. And ideally, we want to do this with a plan in mind. We don't want to let different teams dealing with the network independently, but we would like perhaps the architects, the platform team, to be providing this to the teams. The teams don't want to manage the network. The teams want to think of what matters. And what matters is the product, the customers, the users, not the network. The architects are going to be providing the underlying infrastructure that deals with the network, among other things. And in this new world, in this new era, there are going to be challenges that we have to address in order to be successful. Some of them are, for example, identity. We want to identify the workloads that are running within our system. They don't run all together in a monolith anymore, in one single code base, but they run in a decoupled way. So how do I identify these different systems that are trying to consume each other? We want to be encrypting that network so that nobody can listen to it, nobody can fetch information from the network itself. We want to be able to route requests from one service to another, and also from one version of a service to another. We want to be able to observe the network. We want to be able to trace and log all that's happening within the network for a couple of reasons. Now that we have more moving parts, it is harder for us to understand when there is a problem, where the problem is exactly. So we want to be able to trace these requests from service A to B to C, from one data center to another. We want to be able to use that information to improve the services over time, to make them faster. Performance becomes much more important because it compounds over time. Latency gets bigger over time. Performance, it's not nice to have anymore. It's a requirement for decoupled and distributed architecture. So as we transition to more decoupled systems, we want to be adopting technologies like mutual TLS for obviously encrypting the traffic, but first and foremost, in order to identify the traffic. The certificates identify the clients, the services that are consuming other services. And we need to do that in order to, on top of mutual TLS, being able to implement other functions like routing, for example, or tracing and observability in order to know what service is consuming another service, who they are. Identity. We want to be able to segment the traffic so that we determine what services are allowed to consume other services. We don't want to put hardware there. We don't want to have firewall. We want to define all of these via software so that we can secure the architecture by preventing services to consume systems and databases that they should not be using. And by the way, a service can be a workload, can be an application, but can be a database as well. Postgres would be a service. Kafka is a service among the other services we have. The latency, like I said, compounds over time. If we have 10 milliseconds of latency between one request and another, in a decoupled and distributed architecture, that doesn't stop at 10 milliseconds or 100 milliseconds. It gets bigger and bigger over time because service A consumes service B, C, and D, and then all the way back. That latency will compound. And latency really becomes like security. They say security is not a feature. Security is something you build since day one. Performance ends up being the same thing. It's not something we can add later. We have to build systems to be performant since day one. That is important. Routing. We want to route across different versions. We want the teams to be able to experiment with new features by redirecting only a subset of those requests to a new version. We want to reduce the risk into creating new services, creating new features when we roll them out. Why? Because if we roll out a bad version, then we make our existing customers unhappy. And if they're unhappy, they will leave the product. And if they leave the product, our business will get hurt. It's all about the business. We're building these things so that we can scale the business in better ways. As well as error handling that can deal with the network, can deal with the uncertainty of going from a safe place, the monolith, the CPU, the virtual machine, into an unsafe world. And of course, logging, metrics, and tracing so that we know what's happening within the system. The more services we have, and the more logs and metrics we'll have to monitor. Otherwise, we would be blind to what's happening within the architecture. There are patterns and technologies that can help us build all of this. Likewise, we don't want to build our own data center anymore, and we use the cloud. We also don't want to build our own network management. We can use existing technologies that help us with that. For example, if we look at the basic connectivity between one service and another, we could adopt patterns like service mesh that introduce an out-of-process proxy alongside our services to be dealing with all those things I just mentioned: identity, mutual TLS, security, observability, and routing. The alternative is that if we don't outsource those functions to something else, then we have to build them ourselves within our systems, right? And that opens up the risk of different teams implementing these functions in different ways. For example, LinkedIn does not use any service mesh sidecar proxy pattern, but they have a smart Java client that every team needs to use in order to be able to consume another service. That means that LinkedIn cannot move away from Java, from the JVM technologies, because the moment they do, they will have to replicate those functions. They will have to replicate that smart client in a different language, and eventually that creates fragmentation. And so if we do outsource everything to a sidecar proxy, now the sidecar proxy becomes the component that connects with another sidecar proxy belonging to another services. And the contact points are among different services. It's not the service itself anymore, but it's the proxy, this out-of-process system that then deals with that connection. This has the benefit of allowing the developers who are building the services to not worry about any of that. They build their service and they assume the network is always going to be reliable for them because something else is taking care of that, the proxy. And because we don't want to have one proxy for many services running on a virtual machine, because if that one proxy goes down, all the services in that virtual machine also become inaccessible, we want to be able to replicate the sidecar proxy for every instance of every service that we have deployed in our infrastructure. That means that if something happens on one of those proxies, the service as a whole will still be consumable because other sidecar proxies will be available then, as opposed to having one for many instances of our service. And you might have heard of this. This is the typical service mesh pattern. And the more services we create, the more sidecar proxies we create, the more complex it becomes, though we introduce new challenges, the more complex it becomes for us now to instruct and orchestrate and configure all of the sidecar proxies. That's why we need a control plane that can allow us to manage and configure these proxies. At Kong, we've been working a lot with the open source community into understanding what's the best way to be building this. Something that's not specific just to modern architectures like Kubernetes, modern platforms like Kubernetes, but can also work for existing platforms, virtual machines, where the business is running today, so that we can improve connectivity not just for new greenfield applications, but brownfield applications as well. And so we've been working a lot with the community, and we built open source products, and we're leveraging open source products to build modern service mesh architectures. You might have heard of Envoy. Envoy is the de facto proxy data plane for service mesh architectures, built by Lyft, leveraged by Google and hundreds of other organizations. Envoy is on the execution path of all of the requests. And then to configure those requests in a platform agnostic way so that we can support every team in the organization, we can use a control plane. And among these control planes, we have open source Kuma, for example, fully open source, that the community has been using to configure those Envoy proxies. The idea here is that we need to have a component that's able to instruct the sidecar proxies with features and policies. When we look at the service mesh architecture, we're looking at lots of these data planes alongside each one of our services, talking to each other. The data planes then become the contact points. And the main premise of having sidecar proxies alongside every service is that the latency between the actual service and the proxy, it's always going to be minimal. That's why it's called sidecar. Sidecar just means we're going to be running this on the same underlying virtual machine as the service, so that when the service wants to make a request to the outside world, it goes to this proxy. But this proxy, because it runs on localhost, will always be reachable, and the latency will be minimal. It is an extra hop in the network, but within the same virtual machine. Then the sidecar proxy can take it from there and make the request to the outer world. Another proxy will receive that request. When these two proxies establish a connection, they can now exchange tracing information, observability, they can enforce mutual TLS without the services that we are building having to do any of that. And we're going to be having, like I said, one instance for each instance of our services. Then the control plane configures all of that. It allows us, the architects, the platform team, to establish all the configuration we want to enforce in our architecture. We can now rotate mutual TLS certificates, which are being provided by the control plane. We can now collect observability metrics from one place and then store it in our logging system of choice. We can enforce traffic permission rules and enforce routing rules that allow services to talk to different versions of other services. The service mesh is primarily being used for east-west traffic, traffic that happens within the same data center. But sooner than later, we're going to be having external requests coming from the outside world or from another data center that want to enter the mesh and consume those services. And for that kind of traffic, north-south traffic, we're going to be having the traditional API gateway. Service mesh enables better networking and security within east-west traffic. And the gateway enables governance and onboarding for services and people and developers and clients and mobile apps or IoT devices that are coming from outside of the data center. And it gives them a way, a door, to enter that mesh from the outside. So in the context of open source software, at Kong, we've been working with open source technologies like Envoy, like Kuma, to provide this full stack. This is a pattern. It's not a technology. You can, of course, implement this in many different ways. By 2030, we're going to be having 1 trillion devices connected to our data centers, to our systems in the world. The information will be more and more in motion. And in order to support this future, we must be ready into taking care of connectivity that would allow us to finally build the next era. So to summarize, our products are becoming cloud native. because we want to drive more business and we want to stand on the shoulders of giants. As we become cloud native, we have more connectivity among our services, our clients. And that is a problem. We want to be able to fix that. It can be overwhelming. But there are patterns that can help us, like service mesh, microservices, that can help us make that connectivity reliable again so that we can build and get ready for the next era. Thank you.